All right, folks. So a very quick recap of what we did in autoencoders. We realized that autoencoders are a neural architecture that, for example, you can build with either a fully connected neural network or with convolutional and deconvolutional layers. In any case, there are two kinds of autoencoders. The quintessential picture that people have in mind is that is one in which you sort of create a bottleneck. In the bottleneck, you have a latent representation, and then you have so the encoder encodes data into a usually a lower dimensional latent representation. And then the decoder sort of decodes the data, the lower dimensional representation, back into the data. That's your basic garden variety autoencoder. Now, there are variations to that, many variations. Or for example, and the most basic variation is that you don't do it in one shot with just one layer. You have lots of hidden layers. Or if you're doing convolution, there are lots of convolutional layers. And then in the encoder, and there are lots of deconvolutional layers in the decoder. Right? So now, while that is true, we also realize that we can use the autoencoder for all sorts of things. You can have a reconstruction loss to basically train an autoencoder, we do know. And we talked about the bottleneck principle, how it forces a neural network to learn good representations. There were also a kind of autoencoders, which we call the overcomplete autoencoder. So instead of the bottleneck, you could instead have a layer, which is a hidden representation, whose dimensionality is more than that of the input layer. Then you do have a risk that the neural network will just learn to copy data from the input to the output. And so you need to have some trick to prevent that from happening. The way you prevent that from happening is you can enforce a sparsity measure. You say that no more than a certain number of, for example, latent dimensions should be active. Others must be zero. That's one way of doing it for a given input. So you can apply sort of penalty to that. That's one way people do. The other is you can put a limitation, L1 regularize. You say the absolute size of all of these activations must be below a threshold. So there are all of these things that you can do. The other trick, another one that is very useful, use of autoencoder is for denoising. It is quite interesting that it figures out a way to denoise input data. If you take input data, you perturb it, you introduce noisy perturbations to it, and then you feed it to a autoencoder, and then you say the loss function, though, is with respect to the original image. Then what happens is the machine is forced to learn what is the clean data manifold from which data is taken. It is forced to learn the actual data distribution. Very, very interesting that you can do that. And as you will realize, it had some resonance with things like UNet, which we haven't had time in this course to discuss, but we discuss it in the boot camps. Anyone remembers that from the boot camps? UNet. Okay. So we do that. So now we have the contractive autoencoder, which basically says that your machine, your autoencoder, must be completely, the latent representation should be invariant of the small perturbations of the input. So if you do a Taylor expansion, if Z is the function of X, and you introduce a perturbation delta, small perturbation delta, what you're saying is Z prime should essentially be Z. And that is only possible, like if you do a Taylor expansion of this, it is only possible if the gradient of the function, right, with respect to x is zero. In other words, with small perturbations, the gradient doesn't change. It's practically zero. And the way you enforce that is you put a loss function that is on the Frobenius norm of the Jacobian. Now, that sounded like quite a scary mouthful, but I hope the intuition we brought to it stays with you, that all we are saying is that all the partial derivatives should be zero because the function should be invariant to perturbation on any of the axes of the input. Right? That's all it is saying. So, in other words, what we are saying is, if the data is given to you as blue dots, the machine should nonetheless discover the yellow line, which is the data manifold, and be able to predict points on the closest points on the line, which are the orange dots. Do we remember that, guys? As a denoising effect. That's a classic denoising effect that we did. Well, we went through many things. Then we came to variational inference. Variational inference, we tried to do it in the word inference comes from the fact that sometimes something is hidden that's driving observable. We took the example of a pot of water that you're boiling. What you may see is the volume of steam, right? Outflow of the volume of steam per second. How much steam is leaving per second? But the generative force is actually the temperature, the heat, not temperature, the heat that you're feeding to the pot. The more heat energy that you're feeding to it, the higher will be the observed steam flow. Isn't it? And so suppose you couldn't see how much heat you're feeding it, but you suspect that is the cause of steam leaving a pot. What you're saying is your heat or your energy is the latent variable Z, and X is the steam outflow. And so you hypothesize that there is a relationship between Z, the heat intensity, and the steam rate or volume, isn't it? You expect that this is there, and therefore there's a function. The steam is a function of the heat intensity, the steam rate, right? And the converse of that, therefore, in the reverse direction, therefore, you ask this question, by observing the steam rate, can I infer how much heat is being fed in? Right? And that would be the G of Z. The word inference in machine learning, more strictly speaking, refers to this. It is the modeling of the latent variable that leads you to that sort of, you try to build the model G, right? That if X is the observed, how much was Z? And it's been put here, if you look at this picture, with a dotted line. This is your classic Bayesian inference. There is a whole world of theory called Bayesian inference. These days, it's gaining a lot of attention in new inputs because it turns out that hyperparameter optimization is best done through Bayesian optimization. And there, all of these theories come in quite a bit in a big way. Bayesian machine learning is itself a very fascinating and deep field. It contains marvelous things like Markov chain Monte Carlos and other things, the Gibbs sampling, and the Metropolis algorithm. Do these words ring a bell with anyone? They do. Yes. Yeah. And Roman, which word?
The beginning of the last data.
The Gibbs sampling and so forth. So let me give you guys a sense of how important it is with a little aside. If you were to ask which was the most important algorithm of the 20th century, most serious researchers, if you say which was it, especially in the field of machine learning, but broadly in all of computer science, arguably a lot of computer scientists, a lot of researchers would say it was the Metropolis algorithm. And it's a shame that they don't teach you in computer science courses. It speaks to the absolute dysfunction with which computer science is taught in universities everywhere. But anyway, those are all metropolis algorithms and good sampling and all of these things you do in Bayesian machine learning, Bayesian probability. But we'll leave that aside. The way we'll bypass all of that and we say that from a practical purpose, from the perspective of autoencoders, what we say is that, see, we wanted, if you just put a reconstruction loss that the output should look like the input, what the machine will do is it will say, all right, my goal is to optimally reproduce the input, isn't it? And so I can put points, let's say green points, red points, blue points, wherever I want in the latent space. I can just separate them out or do all sorts of funky things. And when you do that, what happens is your latent space has a few problems. Sometimes points that belong to a class, let's say the green dots, input green dots, do you notice that they are literally in two clusters? They look as though they are in two clusters. Some other thing is there's a lot of overlap. The third thing that happens is there's a lot of empty space in the latent space. So that if you pick a point from there and you ask the decoder to decode it, it wouldn't have an idea what to decode it. That's a problem with that. And so what you want to do is you want to have a dense sort of a spread in the latent space. You want all your points to get projected down, perhaps close to the origin, in such a way that you could have, one region for broccoli, one for rice, one for soap, etc., as I mentioned. But broadly speaking, if they are very tightly packed, there are many benefits to be had because I can sample from any point there in that circle and know with confidence that the decoder will decode it. It knows how to interpret it. The second thing is I can do vector calculus on that, vector arithmetic on that. I can go gradually from broccoli to rice. Right? A plate that is mostly broccoli to a plate that's mostly rice, maybe with a little bit of broccoli in between, and so on and so forth. You can do all sorts of games with that. Those are huge benefits. Variational autoencoders were so good, actually, that after a little while, once they were discovered, they took over the world, essentially. Now, how do you do that? The way you do that is through a process called, by measuring the way the machine initially tries to spread it out and the way you want it to be. Right? So these are two distributions. The way you want it to be is like a bell curve. The way the machine would optimally keep lowest reconstruction loss is by putting it like this. And so you give both the loss functions. You say, hey, go and spread out. I mean, get a good low reconstruction loss, but at the same time, make sure that things are clustered around the origin. Right? They have a bell curve. They have a normal distribution. Right? Generalization of bell curve is a normal distribution. And so when you put a double constraint on it, then what happens is you penalize it for not looking like it. One of the oldest ways to measure how different is something from something else in probability field, in the world of probability distributions, is the KL divergence. It is not a distance measure, it's not symmetric, but it's pretty widespread. Now, we talked about it of the forward KL and the backward KL. The forward is mean seeking, the backward is, and so on and so forth. We are not going to rehash that territory again, but the bottom line is if you write your loss function, roughly speaking like this, then you have the best of both the worlds. You have good reconstruction loss, reconstruction of the data. At the same time, the distribution looks fairly compact around the origin. That is it. We also talked about the fact that in subsequent time, the distribution, the method people use to observe the distinction between two probability distribution, they started using Wasserstein distance rather than KL. So in practice, like Wasserstein looks very technical. But my advice, recommendation to you would be that in most situations, the Wasserstein distance will do a better job. So it's become pretty prevalent actually to use Wasserstein. Sometimes people will colloquially say, oh, we can measure it with KL divergence. But when they actually sit down to code, what they will code is the Wasserstein distance. Now, what is Wasserstein distance? It is basically the earth mover distance. Remember, we said how much earth do you need to move to change one probability distribution into another, or I call it the sand mover's distance. If you think of each probability as one unit bucket of sand, is spread whichever way you want that probability distribution wants in space. Right? Like, for example, if your children play on the beach, it's a very simple intuition. So that is that. Now, vector quantized VAE solves a different problem. But anyway, this is it. When you can do that, the beautiful thing is that you can sample off the posterior, or sample off the distribution, the latent distribution, and do that. Now, one part about variational autoencoder that you do is a little interesting. What you do is, suppose the encoder encodes it to a point Z. Right? You don't give that to the decoder. You actually find some point in a close neighborhood of that point, Z. And you give it to that and you ask the decoder to decode. But if it has to decode it to exactly that, let's say a 9 has to be land somewhere, but you give a neighboring point and you say decode it to 9. What does it mean? It means that you're forcing that entire neighborhood to be 9. Do you see that? Right? That entire latent neighborhood, you're forcing it to be 9. Right? I hope I'm making the intuition clear. Let me draw it out. Suppose the encoder Z, and Z takes, suppose you give the letter 9. And Z, 9 was, it just came here. Right? But suppose you say to the decoder, I'm not going to give this, I'm instead going to give this point in the neighborhood and ask the decoder to produce 9. Still produce 9, right? Then what will happen? The only way the machine can produce it is if it can make sure that this whole neighborhood belongs to 9, belongs to 9s, all sorts of 9s. Does that make sense, guys? And that is how a variational autoencoder forces regions to come together. Right? It prevents it from just occupying non-local regions. So that's how variational autoencoder works. But it does have a problem, something called posterior collapse. Posterior collapse is if the decoder is very powerful, or if you're not too careful with how strongly you focus on KL divergence versus how much you focus on the reconstruction laws, you can end up with a situation where the machine just ignores whatever input comes and it produces whatever it likes. You see it because it will keep on producing repetitive things. It's a problem. And so I ended the class with a little bit more advanced topic, vector quantized variational autoencoders. And I brought in the point that you could actually force it to just match a vector in the code. One analogy for vector quantization is, see, whatever you write, we human beings do that intuitively. And maybe I don't know if I mentioned this intuition or not, but I'm going to do that now. See, suppose I write a sentence like this. Would you agree that I could, irrespective of all the T, H, etc., I could say that this corresponds to a vector that stands for T. This corresponds to a vector that stands for H. This corresponds to a vector this is, just replace it with that vector. Does that make sense, guys? And the English language we are able to function just fine with 26 letters, right? Or 10 digits and a few symbols and a few punctuations, isn't it? It's a very limited vocabulary. Nonetheless, it does not limit in any way the expressiveness of the language. And so in vector quantization, that intuition is very much there, that so long as you write it up, it's almost like taking shorthand of the picture. A picture comes in, right, of a cat. And what you do is you, for each of the feature map, you basically say, what is it closest to? And you may say, this is T, this is H, this is E. I'm just giving an analogy here, right, to this. And you just remember what it is. Then you would agree that this contains fairly reasonably what the input was, right? So it's sort of a hand waving analogy to get the idea of the vector quantization. All right, guys. So that is the summary of or a review of what we did last week. Any questions before I move on to the next topic, to the next generative model? And do you guys realize that the variationals are generative models? Why are they generative models? What makes them generative? Because you can sample off the latent space. You know, it's a very compact space. You know that every point around the origin will decode to something useful. So you don't have to just pick a point that was actually there in the training data. You can pick any point in the latents, right? And how many points are there in the latent space that are meaningful? Infinitely many, isn't it? They happen to be close to the origin, let us say, but there are infinitely many such points. Go ahead, Roman.
Does that mean the further you get from the origin, the more likely it would be to hallucinate?
No, I wouldn't use the word hallucinate, but the more likely it is to produce something that will look less realistic. So, for example, it might produce a Roman, but it might have two horns on its head, like a cow. Right. So it's like that. All right, guys. So with that, any more questions for Sandeep?
One question. So I don't understand the last diagram. There's a cat, and you have written the.
No, this is just an intuition. What I'm saying is, it might put some, like there are these vectors, 512 vectors, right? 512 vector code book. The language is called the code book. And a code book, a very simple way of thinking of a code book is, it is basically your vocabulary in some sense. So every feature map, so when you do CNNs, what do you end up with? A lot of feature maps, right? And each feature map, you're basically saying, pick one, pick a vector here. Which one is it closest to? And note down that vector. Maybe this was vector 7. Maybe the vector or some vector. So I'm putting A, D, etc. Right? Just to illustrate the point. Any other questions, guys?
Asif, could you confirm what homework was expected from last week, please?
Last week, actually, I don't think I gave any significant homework. Anyone? I just asked you to play with, for example, this person does not exist and so forth. Isn't it? Last week it was a little advanced topic, variational autoencoders. So I thought in the introductory course, it wouldn't be appropriate to give any substantive homework. I covered it because it is necessary to cover it, but because I felt it was a bit advanced, I didn't give it.
Okay, thank you.
As you see, 512 vector means like this. 512
is the code book. It's a vocabulary. Pick one.
512
is a constant.
512.
Yeah, 512 possible vectors are there. You just pick which one is it closest to. That's say that again. Yeah, that is it. So what you say, it's like, think of these vectors as, these are called code book vectors. So suppose I have a vector of whatever dimensionality, let's say dimensionality d, right? Think of it as 64 dimension. For example, each vector is 64 dimension. What is it? So you're basically saying that it is this or A, B, this. And whenever a feature map comes, you ask which one is it closest to. That's all.
What does the mapping, does the encoder, the decoder to mapping to the whole bit?
It is the once the encoder. So the way it goes is the encoder will produce a function of x. It will produce an embedding vector, right? Let me call it e. It will produce that, or let me call this vector for some reason v. Now what you say is that I'm not going to look at v. I'm going to replace v by something in my this code book, e to the e, from this library of 512 vectors, I just have to find out which one is this closest to. Let's say that this is closest to E121 as an illustration, right? So then you would say that Z, which is a latent vector, is actually E121 for this feature map.
You're doing a cosine distance here to find out.
Yes. Actually, not cosine. The dimensionality is, yeah, you could do cosine distance, but generally they just do direct Euclidean distance.
Basically,
Yeah.
dot product.
Not dot product, Euclidean. Like you would do V minus E. Right?
And that is done where? After doing the encoder or decoder, or is that?
No, between the encoder and the decoder, right after the encoder. So you have extra things happening after the encoder. So anyway, guys, VQVA, the only reason I mentioned to you this topic is it is very, very important, this line of thinking. In fact, the first DALI implementation, remember that chair looking like an avocado and a tutu or something, daikon taking tutu for a walk or something like that, a dog for a walk. All of those things were created using something that's very, very close cousin of the VQVA. But we'll come to that in due course of time. This was a review of last time. Any more questions, guys, before I end the review and move to topic of today?